Coming back to our thing, which is about unitary transforms, coming back to UTs, okay, what did we have? We had a situation somewhat similar, right? We had a V which was some AU, A transpose, we had V to be unitary, right? U was our image. So now what this means is that, because right, when we arrived at this, we arrived at it independently of anything else, right? So which then means that I can actually rewrite this expression as a vector V as A Kronecker A multiplying U, right? And now suppose I indicate this as script A, right? In order to say differentiate it from the original A, right? That is the 1D unitary transform. Then this becomes A times U. So now if you see, right, this has the same form as you would have liked. For example, in 1D, right, you had like V is equal to A U, no? Okay, whereas when you saw an image transform, it looked like this. Okay, but then if you kind of work your way around through a Kronecker product, then it turns out that you can actually have a form which you're already familiar with, but then whatever held for 1D, right, also suddenly holds for, actually, if I had a video, right, suppose I had not just one frame. See, in this case, right, this is like you had a 1D sequence, right? From there you went to an image, and then you said, so your interpretation is that your 2D basis images are all sitting in this guy, in the script A. Okay, so this so the point is, right, so the script A, right, will contain the basis images and all, right, and those basis images themselves are coming from your 1D basis, right, because the 1D basis we know, right, it is all sitting in A, right? Whatever A, you can basically show that they are sitting in A Hermitian, right, or in A, whichever way you want to look at. Okay, now the point is, right, what does it mean for us? So for example, if I told you now that instead of a 2D, suppose I said extend it to actually a 3D case, what would you do then? Suppose, okay, now the same thing, suppose I had an image, let me say, which is M cross N. What would be your formulation now in order to compute, right, let's not even worry about Fourier or something. I have some unitary transform and I want to kind of use that A to kind of go into a transform domain, right? So if for that A, if I wanted to go to a higher dimension, which is from a 1D to actually a 2D, I would say I'll do V. Okay, maybe I should write it a different color. So V is, what would I do? I'll say A which is which is of size whatever, right, M cross M, Kronecker B, right, which is of size N cross N, right, multiplying U. Now instead of this, right, if I had right, with respect to time, I had a this one, a video, okay, with respect to time, let's say I have kind of M cross N cross K clips, K frames I have, and I want to compute, right, a 3D this one, a unitary transform. What would you do now? It's straightforward, right? Straight away you should be able to see it. What would you do? You'll do A M cross M, then take Kronecker B N cross N, then take Kronecker C of that dimension. And so you'll do A M comma M, Kronecker B N then Kronecker, let's say some C, K cross K. Because when you take a video, right, you can't assume that you will have as many frames as you have the size of the image. No. That's why I thought we'll, till now I said square because it's easy, but then if I want to extend it to, one more dimension, along time I can't say take, as many rows and as many columns along K. You may not have that many frames along K, right? Along time you may have fewer frames, right? You may have 10 frames, 20 frames, but then if you wanted to compute a transform, right, it simply means that, so this entire, so this equipment is available to you, right? So right, so basically that is why this is very elegant. Okay, suddenly, right, you see that going from a lower dimension to a higher dimension, whatever 4D, 5D, it doesn't seem to matter at all anymore, because starting from that 1D, right, starting from that 1D transform, everything seems like, it's just one walk away. Correct. So you see the strength of this framework, right? If you work through summations and all, you won't see the strength at all. That's the reason why I said we'll spend some time on this, right? It's okay. You're going to go through this, because this way, right, you'll be able to appreciate the structure much more. It's all so very tight, right? Nicely coupled, and then you don't want to miss all of that. Anyway, right, I wanted to tell it much later, but then I thought, okay, maybe right now is the time to tell it, right? So that you at least realize that, right, you're doing it for a reason. Okay, now coming back, Okay, now suppose I ask you, right, what can we say about A? Now, can I write U as A in no, script A inverse V? Does script A inverse exist? Now, how do we show that? Let's say A inverse, right? What is it, right? If it were to exist, this will be A Kronecker A, right? Because we know the script A is A Kronecker A inverse. Okay, now if you kind of go back to the Kronecker property, this is the A inverse Kronecker A inverse. Right? But then A inverse we know, already A inverse exists, right? Because we came from 1D, so that we know. This is A Hermitian. Okay, A Hermitian Kronecker A Hermitian. Okay, and then if you again go back and use that property A Kronecker B, if you take a conjugate A Kronecker B transpose, this will be simply A Kronecker A whole, this one Hermitian. But then A Kronecker A is what? Script A. Okay, so it means that so whatever happened there suddenly seems to be happening in a very straightforward way here, right? A Hermitian, just as you had A Hermitian to be the inverse of A, script A Hermitian is then the inverse of script A. Right, so of course script A inverse exists, and then you can of course solve for U, right? And only thing is, right, U is kind of sitting in a slightly sort of a different form. That's all, right? Doesn't matter, but then it makes it so much more easy for us to analyze things, because once you obtain your U, you just have to stack it back. Take the first n entries, put it as a first row, take the next one, put it as a second row, and then you are done, right? Whatever rectangle, square, whatever, right? Whatever size it might be. Okay. Now, if you kind of go back to that example, right? Okay, let's kind of go back to that example. What did we have there the other day? We did, right? So what was that example? Let's just solve that example again, but now using a 2D unitary transform straight away. Okay. What was that example? We had A, right? We said this is a 1D unitary transform given as 1 by root 2, 1, 1, 1 minus 1. Right? This is, and then we said our U is 1, 2, 3, 4. Okay, now you know what? So the point is, right, you still have not seen where the A star KLs are sitting, right? Where did they all vanish? Okay, you had the basis images, right there. I mean, it was so very apparent that you could actually take the inner product with basis images, and all. It was all very clear. Now here, it's not immediately apparent where they are sitting. Is there somebody who can tell me where they are sitting? Where should they be sitting? Just apply the same analogy, right? Nothing will change. Whatever happened there will happen here, right? That is the strength of this formulation. What was happening there? Where were the 1D basis images sitting? Okay, anyway, right? So we'll see that one. But we showed it, no? Where was your A star K sitting? Where was the basis image, basis signal, 1D signal? Where was it when you did a 1D? I mean, you took the A matrix, took the A, this one Hermitian. The columns of A Hermitian contained the basis, no? That's how we started, right? We said A Hermitian, take A Hermitian, take the columns of A Hermitian, they form an orthonormal basis, right? Inner product A K star A L star is equal to, right, 1, whatever, if K equal to L, L 0. So now, given that 1D basis signals, if you want to call them, came from the columns of A Hermitian, then where should the basis images for a 2D transform come from? Script A Hermitian, from the columns of script A Hermitian. Same thing should follow, no? I mean, something should be seamless, right? So we'll see that. Okay, so that's why I thought we'll revisit that example. Okay. So let's write down. Okay, script A first. Script A is what? A. Right. A Kronecker A. So what do you have? A Kronecker A is what do you have? So 1 by root 2, 1, 1, 1 minus 1. Take the Kronecker with 1 by root 2, 1, 1, 1 minus 1. Then you will get 1 by 2. What do you have? 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, minus 1, minus 1, minus 1, 1. Okay, this is A. So A Hermitian, in this case, if it's symmetric, right, it won't matter. This is actually symmetric. 1 minus 1, 1 minus 1, right? 1 1 minus 1 minus 1, right? So it's actually the same, okay? But anyway, write it down. So that, right, because for this example it is the case, but then for some other example it won't be. 1 minus 1 1 minus 1 1 1 minus 1 minus 1 1 minus 1 minus 1 1. Okay. So now if you see, right, so the first column of this one, A Hermitian, okay, which is all this is independent of the image itself, right, because you have a basis now, because you know what we are talking about is all a data independent transform, right, it is independent of whatever you have. So if you look at the basis image, can you see, check your first A star 0 0, which was your first basis image, what was it? It must have been 1 by 2 1 by 2 1 by 2 1 by 2, right? Can you just go and check? This is what it must have been. Okay, your A star 0 0. Okay, and that you see is sitting right here. Just that it's, you know, it's sitting in the form of a single column, a vector. But you know, if you take the first two guys, put it as a first row, take the next two guys, put it as a second row, you get your A star 0 0. Then claim is your A star 0 1 should be this guy, 1 by 2 minus 1 by 2 1 by 2 minus 1 by 2. Please check that the second guy should be your A. So this should be your A star 0 0. This should be A star 0 1. This is A star 1 0. This is matching. Should match with what you had that day, no? 1 0 is 1 1 minus 1 minus 1, and then you have A star 1 1, which is of course 1 minus 1 minus 1 1, right? Sorry, 1 by 2 has to be there. Okay, multiply by into half. Correct. So all this should be exactly the same as, you know, what it was there. I mean, except that, right, you don't have to walk right in that manner. Okay, out of all these 4 or 5 ways, right, in which you can write, the most elegant way to write it is this form: V is equal to script A times U, because whatever was happening there, right, all of that is immediately apparent here. I mean, so you can see a straight mapping between whatever is happening in 1D can happen in 2D, can happen in 3D, can happen in 4D, and so on. Right, you don't have to struggle to see what will happen if I want to extend this transform to this one, higher dimensions. Similarly, the basis image interpretation, the orthonormality interpretation, everything is laid bare. Okay, and you know, in fact, almost identical to whatever happened with the 1D transform, right? Which is what I said all the while, that our focus will be to start from 1D and then not worry about whether looking at DFT, DCT and all, but then create a framework wherein you just throw in whatever you want, and then all of that should just follow. Okay. And now, for example, if I wanted to solve for V, which is my transform coefficient, I will do A times U. Okay, so this is my A matrix, right? So suppose I multiplied it with okay, so what is it? U again I'll have to stack it 1 2 3 4. Correct. So my U, you go back to the U matrix. Okay, so if you stack it up as this vector, now what will you get? So what do you get? So A is this guy. So let's say we just keep this 1 by 2 out. So 1 plus 2 3 10. 1 minus 2 is minus 1, plus 3 is 2, minus 4 is minus 2, then 1 plus 2 is 3, minus 3 is 0, then minus 4, and then 1 minus 2 is minus 1, minus 3 is minus 4, plus 4 0. So then this should be 5 minus 1 minus 2 0, or the matrix V, right, if you want to put it in a transform, you know, in the same way, right, that you would rather probably see it as an image transform, will be 5 minus 1 minus 2 0, right, which is what you would have got. Okay, at that time also when you did AU A transpose, right, this is what you would have got. So V is equal to AU. Okay, so this is A star 1 1. After this, I think what we do is we take up like one transform at a time. Okay, so what I thought is, right, we won't do all of them, there's too many of them to do, right, because you just want to know how this works. So we'll start with a DFT. Okay, and you see, until now, right, okay, no, yeah, one more thing, right, you see, right, the other thing, right, which you would again want to, if you see, I had said that there are actually 3 properties, 1 2, and then the third one, right, we still have not seen the impact of the third one, which is about doing a diagonalization and all, right. Till now I didn't kind of talk about any of that, right. I've only kind of hovered around 1 and 2. But then this third property, right, which is a diagonalization property. Okay, this is a diagonalization. This is implications for both a system matrix and for a covariance of the data. Okay, for both it will have implications. Okay, so the point is, right, we would like to see as to know as to what kind of structure this A acquires, when you do a 2D transform. Okay, we would like to see, for example, if you go through a DFT, right? Go through a DFT and suppose you have this A matrix for that. Let's call this as phi. Okay, then we will see, for example, then the idea is that, right, what is the impact of phi on on this matrix of a certain kind, which is, let's say, which we know for an LTI system, which is circular in nature. And similarly, if you think of a covariance, which is again circulant in nature. I mean, have you seen kind of random processes which are circulant, what are called cyclostationary processes and so on, right? Some of you have heard about it. So for such matrices, for such data, right, what are its implications? And then similarly, right, if you come down to actually a DCT, okay, so we will first look at a DFT, right? We will not, right, I won't spend too much time on all the DFT the way we do in signals and systems, right, or every property, we are not interested in all of that. Okay, we just want to see how we can compute it, right, from, let's say, 1D to 2D, and some simple properties that some of the many of them are simply the same as what you have in 1D, but then in 2D there are certain nice things that you want to know about. We'll talk about that. Then we move on to a DCT. And then here again, right, we will talk about where its implications are. So DCT has more implications here, okay, on what kind of a covariance, right, will it actually impact. And we will see that, right, it will be more impactful than phi. Suppose we call this as A is equal to C, right. Now this matrix will have to keep changing. Okay, as you walk from one transform to another, this A will start changing. So for DFT it will be phi, for, let's say, DCT it will be A, will be C. DCT is all real, by the way. Okay, whereas DFT we know is generally not real, right? 3 cross 3 and all is not at all real. Okay, and okay, now there is one point I forgot to tell. Right, what will happen? See, for example, I have this expression. No, I wrote down V is equal to A. Okay, script A times U. Okay, now it would have at least struck some of you, right? Some of you would have this doubt. What if I take the A matrix, which is actually a 1D unitary matrix, right, unitary transform. Suppose, let's say, U is n square by 1. Suppose you take a square image, right, it's n square by 1. So I've stacked it up as this vector. Suppose I take A to be of size n square by n square. Would it then kind of give me a 2D transform? So you see my point. What I'm saying is, see, I put script A here. I said, right, that in turn comes from A. But then you can argue, right, what if I take an A, which is a 1D transform, I have it, I simply take it of the same size as U now. I make it as big as you want it, n square by n square. Now I multiply. Can I claim that, well, that should be then a 2D transform? It cannot be, right? That will be wrong then. Right? If that happens, then the whole thing falls flat. Right? And in this example, were you able to see it? I want to see whether you saw that in this example. What is striking about this? You tell me one thing. This guy, something is very striking about it. It's a very small example. Tell me what strikes you there. The same argument, if you applied it there, what would have happened? If you had a 4 cross 1 image, right? In this case, U was simply a 2 cross 2, correct? Suppose I taken, say, this is a DFT, correct? I mean, DFT, DCT, they all will be the same at 2 cross 2. But imagine that if I had a U which was 4 cross 1, and suppose I interpreted it as a 1D sequence, multiply it with actually a DFT matrix now, which is 4 cross 4. Will its entries be real? You see here, all entries are real. Okay, so this is not the same as taking A or DFT of that size, 4 cross 1 and starting to multiply. It is not that. Okay, so this is an important, please remember that you cannot take a 1D DFT guy and then make its size equal to this vector size and multiply and claim that, right, that should be, then why is that not why is that not a 2D? That is not the way to arrive at really a 2D transform. A 2D transform comes through this one, through a Kronecker product, a Kronecker of A with A. Okay, and one striking example is this, because if you went for a 4 cross 4 DFT matrix, you would have already encountered entries which are all complex, right? You would have had entries here which will all be complex. Forget the first row and first column. The rest of them will all be complex, right? Whereas that's not the case here. Everything is sitting here is real. Of course, even here it will be it will be complex. The moment you go for A, which is 3 cross 3, things can become complex. But the point that I am trying to say is, please remember that, right, that this is not correct. You can't take a 1D transform and think of U as a signal, 1D signal, and start multiplying and then claim that I have this one 2D transform, right? Then the whole exercise is meaningless. Okay, I'll stop here.